In this video, let's talk about how we can actually apply and use those identities that we talked about in the last video. And actually, I did forget to mention this, is that you can do similar constructions to show the sine of s plus t is equal to all this. It's almost exactly the same math that we did in the previous video to prove this particular part, the sum identity for cosine. And also what I wanted to mention is the difference identities for sine and cosine can actually be proved from the sine identities, from the sum identities, I mean, because if I were to just, like, if I'm looking at the difference between these two identities, the only difference between them is it's instead of s plus t, it's s minus t. So I can always think of minus t as plus a negative t. So really, the secondary angle I could just think of as negative. So if I were to just plug in negative t here and here, well, since cosine is an even function, negative t is equal to cosine of positive t. So I have no sign change between these two terms. But if I were to plug in a negative t into this part here, this would leave me with sine of minus t. And since sine is odd, the negative passes through, or what I would get is a minus a negative. This term would always also be negative. And a double negative makes a positive. And very similar for this part. Essentially, it's the same formula. All we get is a sign change on the secondary terms because each one of those is sine of t and cosine of t, which are even and odd respectively. And then the tangent of these, the remaining two formulas can be derived from these. So, I think just doing this one was enough of a proof. And this is just sort of another thing I wanted to mention too. Last week we talked about proving trigonometric identities, like kind of using our fundamental identities as tools. But you can also prove identities using geometry or using intuition or using other techniques. So that's kind of where these ones come from. It's something I wanted to show you. It's something I'm not going to make you do on an exam because it's very difficult and could take hours just to really think of how we could actually start approaching such an identity. And in the last video, I showed you a geometric proof of the law of the summation identity, the sum identity for cosine, which is definitely not something that, I would expect you to figure out in an hour-long test. But basically, I'm going to try to end that tangent and get into how do we actually use it. And let's start with trying to figure out, as I was saying, what about at 15 degrees? What would be the terminal point on the unit circle at 15 degrees? And how could we do that? Of course, we could use a calculator to do that if we change our calculator to degree mode and just type in the sine of 15. But the question is, what does this number mean? And what's an alternative? Like, is there a way I could figure out what is this? Like, is this the square root of 7 over 5? Like, as we know from the unit circle, we know certain positions exactly. If I'm using a calculator, it tells me, okay, an approximation, but I don't know what is that exact number. Like, it appears to be irrational. But basically, this is a process for doing that. So to begin, let's start with the sine of 15 and cosine of 15 and tangent of 15 degrees. And another thing about this is, well, where do we even start with such a problem? Like, how do I begin? But my point is, it's in this section of addition and sum identity, so we're going to try to use these in some way. And as sort of I was saying in the last video, 15 degrees is actually equal to 45 degrees minus 30 degrees. So, like, just, a very simple arithmetic, right? 15 is 45 minus 30 degrees. So sine of 15 degrees should be equal to exactly that. And, why would I ever think to do this is another question, but that's kind of my point is if I can imagine this angle as a sum or a difference of two different angles, I can use those identities that we just proved and talked about to actually progress. And basically, since each of these angles are our fundamental, special angles on the unit circle, we already know how these behave, and we can figure out how the sine of 15 behaves from these. And then if I apply, since this is a difference of two angles, I want to apply the difference identity here, which would give me sine of the first, cosine of the second, minus cosine first, sine of the second. So let me leave that right there while I write this down. It's going to be sine, or another way you could think about this is if I'm trying to use the identity, I want to know, well, what is s, what is t? And as I apply that identity, I'm going to just make sure to substitute s's and t's into the correct position. So sine of s, cosine of t, Make sure I get the sign SIGN correct, which is for the subtraction formula for sine. It's minus cosine of the first times the sine of the second. And so basically I apply the identity, and what I get is this times this minus this times this. And each one of these things we know directly from the unit circle, because here's 45 degrees, we know x and y, and here's 30 degrees, we know x and y. So sine of 45 degrees is root 2 over 2. Cosine of 30 degrees is going to be my x component, which is root 3 over 2. So now I can evaluate each of those trig functions because I know how to based on the unit circle. Now the cosine of 45 is also root 2 over 2 because remember at 45 it's the halfway point. Both x and y are the same by symmetry. But at 30, how this is one of the ways I memorize these specific positions is 30 degrees is the short component. And so if I'm looking at that point on the unit circle, it's got a short y and a long x. Because to that point, it's further to the x. Sorry, my hands are backwards in the camera. That might make more sense. The x is longer and the y is shorter. At the halfway point, 45 degrees, they're both the same. They both have to be that midpoint. And at the 60 degrees position, y is longer and x is shorter. And since I know there's only 3 values that we have for our special angles, it's either going to be 1/2 root 2 over 2 or root 3 over 2. We know that this is short x, so x is small. Here we got long x is long, and long x is long and short are always paired together. And then in the middle, they're the same. So that's kind of a memory trick to help with the 3 special angles, 45, 30, and 60. But anyway, sine of 30, that is going to be short y, so it's 1/2. And since we're in the first quadrant, they're all positive values. But basically what I now end up with is, well, I have some fractions, a bunch of fractions for each of our trig ratios. And then, well, I have root 2. I could actually multiply these together. Because root 2 times root 3, well, fractions I multiply both tops and bottoms together. Root 2 times root 3 would just make rad 6, because remember, if they're both rooted, you can just multiply the insides together. And 2 times 2 is 4. And then in the second fraction, root 2 times 1 is, of course, root 2, and 2 times 2 is 4. So what I end up with is root 6 over 4 minus root 2 over 4. Or, another way we could write this is because we have a common denominator, root 6 minus root 2 over 4. Or there's even other ways that you can simplify this, but I think that this is good enough for our result. So what is the point and what's the summary here? But my point is we can figure out, well, what is the sine of 15 degrees exactly? So kind of returning back to my unit circle, the sine of 15 degrees, this is no longer an unknown value. We can actually figure out what this fraction is, square root of 6 minus the square root of 2 over 4. And it's not exactly pretty, but it's another thing we know. And once, if we know, say, 15 degrees, we can use that to find something else. And you can kind of, change the identities with each other to solve, well, what about this angle? What is the exact value of this angle? And go from there, which can be quite an elaborate process because this is kind of a it's kind of a complicated number. But let's also figure out, well, what's the cosine of this angle, and we might as well do the tangent while we're on the subject. So let's also do the cosine of 15. And since we know 15, it's going to be the same exact approach. 15 degrees is equal to 45 degrees minus 30 degrees. And so I could then use the cosine difference identity, which is going to be cosine cosine plus sine sine. So I'm going to get cosine. Let me try to make sure it took a little bit too much room there. But I'm going to get cosine cosine plus sine sine. And if you had to memorize this, you could quite easily remember this by the fact that cosine pairs the same angles together, or sorry, the same trigonometric functions together. with the opposite sign. Sine pairs the opposite functions together with the same sign. So I don't know if that makes sense, if you know what I mean, but it's kind of pairing the angles always like the two angles together. But sine pairs up sine and cosine with each other and subtracts, whereas cosine pairs the same ones together but has the opposite sign in between. And since I'm giving you guys a note page for your exams, it's probably not that important that you memorize them and in general, but I think it's more important to, number one, just be aware that these identities exist. And number two, just know that they're helpful. And these are actually quite helpful in calculus for figuring out the derivative and other things with regards to trigonometric functions, because these are more identities. Identities are always useful in various positions. And so your calc teacher will likely reference these identities when you're talking about derivatives. And so, as long as you know it, you're kind of aware that it's there, then it's not like this formula is not something new that's like, what the heck is going on? And it kind of makes sense. Anyways, let's finish this one up. Cosine of 45 is root 2 over 2. Cosine of 30 is root 3 over 2. And sine of 45 is root 2 over 2. And sorry, this is supposed to be sine, isn't it? I'm just noticing that I was talking too much when writing, because it should be cosine, cosine, sine, sine for cosine difference formula. Yes. And sine of 30 is short, so 1/2. And that would leave us with root 6 over 4 plus root 2 over 4. Or, of course, I could write that as root 6 plus root 2 over 4. And that would leave me with the cosine of 15 degrees, which again, that should be the x-coordinate at the unit circle at that position. So I'll go ahead and fill it in here on the slides. Just so we can kind of have it as a reference point. But essentially, we figured out another point, 15 degrees, and basically I could elaborate my unit circle and my understanding of how do I find the exact value of these various points. Now, of course, I could use my calculator, as I said a minute ago, and let's go ahead and check to make sure. Are we actually getting the same thing that the calculator gave me? Because, of course, this should be the sine of 15 degrees as well. Sorry, I don't have my graph here labeled, but this one is the 15 degrees. But that should be equal to root 6. Let me use parentheses here. Square root of 6 minus the square root of 2, all divided by 4, which is what that is. And basically what I'm showing you is that is the exact measurement of the sine of 15 degrees. You can always use a calculator to find these values, but why? That's something that we're often overlooking when we're doing these sorts of things. But there is an exact way of doing it. It just is a little bit technical, and you can actually apply these things to 3 angles and 4 angles and kind of stack them together with other identities to find just about anything you want. But it turns out that there are other approaches of dealing with this too, using more advanced properties in calculus like Taylor series and so on, which if you've ever wondered, how does a calculator get these values? Like, how does it know? Did they program each individual thing or what? There's other ways, there's other interesting mathematical features built on calculus instead. So, and to me, I really love calculus in those applications, but it's kind of all built upon other things too. And these identities are important in calculus as well. And also due to symmetry, since this is 15 degrees away from here, actually we could find these other points at 75 degrees as well. Because notice how if I'm thinking about the y value is exactly this measurement, that would be exactly the same as the x value of this measurement. So due to symmetry, we could figure out 75 degrees, or you could use a very similar approach. But basically, this one's going to be the square root of 6 minus the square root of 2 over 4. And you could basically find a lot more information from there, like we did before, by using symmetry. So anyways, or you know, if you were to do 75 degrees, you could take a very similar approach as to what I was doing from the packet, um, because and like I'll just show you as another hint about like, well, how would I deal with the sine of 75 degrees or the cosine of 75 degrees instead? Well, basically try to think about what is this a sum of? So in this case, that's a sum of 30 and 45. And you don't want to just pick arbitrary numbers like 20 and 55. You want to pick numbers that are on the unit circle that when added or subtracted make exactly that number. So for example, there's a couple more here in the packet. See if you can figure out these values by thinking about what angles could add up or subtract to make 105 and 285. And with tangent of 15, there's two ways you could do it. You could either use this identity, where s and t, you know, exactly as I did before, use the difference identity for tangent, or if you know both sine and cosine, just take the ratio, because tangent is always sine divided by cosine instead. But anyways, that will wrap up this video